and welcome to the MAML Manual. I'm Iris.
And I'm Sebastian.
And today we'll be covering meet number 2, topic number 5, areas and volumes. Let's jump right into it. Alright, here's our first problem of the video. Just a quick thing before we start. Reminder, the date and question number of the past problems are always down in the corner here. Also, this is a calculator active round. We can discuss rounding rules when we come to them. And also, since this is about areas and volumes, there's so many different formulas that you're going to need to know. And you'll see it here, this first problem. I'm not going to cover them. I'm not going to cover all of them. We'll just see them as they come up. But I do recommend if you're able to put any formulas into your calculator, that would be so helpful. Let's get into the problem. A slanted pentagonal pyramid has a base area of 32 centimeters squared. If it stands 3 centimeters in height, what is its volume? Alright, starting off strong, we have a really strange shape. A slanted pentagonal pyramid is essentially just a pentagonal pyramid, but the top isn't directly over the center of the pentagon base. So I'm just going to draw this in case anybody's still wondering what it looks like. So, it's going to be a pyramid, but with a base of a pentagon. So that means all of the sides are going to meet up in a point, just like that. And I kind of drew it a little wonky, so it's perfect. It already looks like a slanted pentagonal pyramid. But that isn't really relevant for this problem because we're given the height. And the way that we find the volume, the formula involves the height. So the volume of the formula of the volume for this pentagonal pyramid is going to be volume equals 1/3 base times height. And note, this is the area of the base. So if you need to calculate that, just do that before you plug everything into your formula. So our base is given 32 centimeters squared, and if it stands 3 centimeters high, so we're given the height, we can plug those in. Our volume is equal to 1/3 of 32 times 3. Now, notice, the 1/3 and the 3 will cancel out to 1. So our volume is just 32 centimeters cubed. So that was pretty simple. You can answer like this, but you never need to include the units. But yeah, there's our first problem. Pretty simple. Here's our second problem. Home plate, used in baseball, is in the shape of the pentagonal region A, B, C, D, E at right. The square with 1-foot sides has 2 right isosceles triangles attached as shown in the figure. What is the area of home plate? Alright, so first we have our square here. It's 1 by 1. We can obviously deduct that that is going to be 1 square foot. So I'm just going to write that up here. So now, let's focus on these 2 triangles. It states that they are right isosceles triangles, meaning that I can draw a little right angle here, and all of these sides, or all of these angles, are going to be the same because these sides are going to be the same as each other, because that's what makes an isosceles triangle. Additionally, we know that these angles are both equal to 45 degrees, because the sum of the angles of any triangle are going to be 180. You subtract 90 and then divide by 2, 45, 45. Alright, so one way we can go about doing this is the way that I thought about it at first, but there is a little shortcut that I'll show you at the end. So, it's a right triangle, so we can just use the Pythagorean theorem to figure this out. Since these sides are the same, I'm going to label them both as x. So we have 1 squared, which is our c squared, is equal to x squared plus x squared. Simplify that, 1 is equal to 2x squared. Divide both sides by 2. Take the square root. That gets you 1 over the square root of 2. Or, because you don't want to have the radical on the denominator, it's going to be equal to square root of 2 over 2. From there, you multiply our base, square root of 2 over 2, times our height, square root of 2 over 2, and then divide by 2. which will end up getting you 1/4. But, so we know that one of these triangles is 1/4. Multiply that back by 2, it's going to be 1/2. Instead of doing that, instead of using the Pythagorean theorem to figure out the side lengths, what we could do is use this little trick. So for any 45, 45, 90 triangle, there is a ratio between the sides. The two sides side lengths that are the same, we're going to label x, like we do in this figure. And we can also know that our hypotenuse of the 45, 45, 90 triangle in relation to x is x times the square root of 2. So, if this side length is x times the square root of 2, all we have to say is 1 is equal to x times the square root of 2. Solve for x. We get x is the same thing, square root of 2 over 2. And so that gives us our side lengths. Then we multiply that together. We're going to get 2 over 4, which is also equal to 1/2, which generally, if you're finding the area of a triangle, you're going to divide that by 2. But since we have two congruent triangles here, we would be multiplying by 2 anyways. So instead of dividing by 2, then multiplying by 2, I'm just going to leave our answer as 1/2. So we add the area of these two triangles, 1/4 and 1/4. So we have 1/2 plus the area of this square, which is 1. So our final answer is going to be 1.5 feet squared. All right, let's move on. Okay, here's the next problem. You might notice that we only did 2 3-pointers so far. Instead of doing 3 3-pointers and 3 4-pointers, I figured that the video would be a little bit more beneficial if we did 4 4-pointers and only 2 3-pointers, because a lot of it is just knowing the right equation to solve the problem. So here's our first 4-pointer of the video. A circle intersects a sphere 7 inches from its center. If the area of the circle is 576 pi square inches, what is the surface area of the sphere? Give answer to the nearest square inch. So this is actually one of my favorite kinds of problems, but it is pretty hard to visualize. So the way I'm going to draw it may seem a little bit confusing, but you'll see how it's going to help us. So I'm going to draw our sphere. I'm going to say that it is this circle. Okay, here's our center, right? And this is the entire sphere. If the circle is intersecting the sphere, it's just going to slice right through the top. So I'm going to draw a line as being the side of our circle, even though it's two-dimensional. Obviously, it's not going to have any thickness, but for all intents and purposes, this is how I'm going to draw it. So here's our sphere. Here is the circle intersecting it. The circle intersects a sphere 7 inches from its center. So I'm going to draw this line here, 7 inches away from the center. The area of the circle is 576 pi. What is the surface area of the sphere? Okay, so we know that the surface area of the sphere is equal to 4 pi r squared, right? Okay, so the one piece of information we need to solve for the surface area is going to be our radius. But we don't have the radius of the sphere right now. So the way that we're going to find it is by using the area of the circle to find the radius of the circle. In order to do that, all we have to do is say, okay, we know that the area of any circle is equal to pi radius squared. So 576 pi equal to pi times the radius of the circle squared. Cancel out pi from each side, take the square root of both sides, and we know that our radius of the circle is 24 inches. Now, given that, we can say, okay, here's our circle. We know that half of it is going to be the radius. So this length from here to the edge of it, to the edge of the circle right here, is going to be 24 inches. So we still have to solve for the surface area of the sphere. So what I'm going to do to find the radius is I'm going to draw a line from the center of the sphere to the outside of the sphere, which is going to be equal to its radius, right, at any point. But I'm going to connect it to the edge of the circle. And by doing that, I have created a right triangle. So, to find the radius here, we could use Pythagorean theorem, but I hope some of you recognize that this is a Pythagorean triple. It's going to be 7, 24, 25, which you can confirm with the Pythagorean theorem. So the radius of our sphere is 25 inches. So now we're looking for the surface area. So to find the surface area, we are going to say that our surface area is equal to 4 pi times 25, which is our radius of the sphere, squared. So we get surface area is equal to 4 pi 625. Surface area is equal to 2,500 in pi. 2,500. So usually they would accept this exact form, but it's asking for us to give our answer to the nearest square inch. So we can multiply 2,500 by pi using our calculator, since this is a calculator round, and we get, and if we're rounding to the nearest square inch, we get 7,854 square inches. I'll write that up here. 7,854. And that is our final answer. Alright, here's our second 4-pointer of the video. Assume that all bears have the same body structure. I know, a weird sentence to start a math team problem off with. A bear weighing 648 pounds stands 42 inches high from the bottom of his paws to the tip of his shoulders when on all fours. How tall does a bear weighing 375 pounds stand? So, this is a really strange problem. Conceptually, it's very difficult, or at least I found it to be so. The one key thing in this situation is that you have to realize that pounds is going to be a cubic value. We need to know that information so we can find the scale factor from the bigger bear to the smaller bear to find the height. And since height is going to be, inches, or inches to the first power, it's not inches squared, not inches cubed, we're going to have to find the cube root of the ratio between the bear's weight to find the scale factor, to find the ratio between the heights, to solve for the height. Alright, so let's get started. We have our 648 pound bear is to our 375 pound bear. Alright, like I said, these are cubic quantities. So, we would take the cube root of both. But first, to make it a little bit easier, I'm going to simplify this. You can divide both by 3, so you get 216 over 125, which, as you know, are 2 perfect cubes. It's going to be a lot simpler now. So that's going to be 6 over 5 if we take the cube root of this value or ratio here. So now that we have our scale factor, or our ratio between the weight of both bears, but the cube root of that, we can say that 6 is to 5 as 42, the height of the taller bear, is to x, the height of our smaller bear. So you can cross multiply, solve for x, or if you see this right away, okay, 6 times 7 is 42, meaning that 5 times 7 is going to be the value of x. So the height of our second bear is 35 inches. Alright, let's move on. Okay, a rectangular pyramid has edges of 6 and 8 and a height of 4. All the lateral edges are congruent. Find the total surface area of the pyramid. Alright, so first things first, let's draw this. I kind of keep that as a little rule of thumb on any geometry, or any other topic for that matter. Drawing things is so much easier than trying to visualize them in your head. At least it is for me. So, I'm going to draw this. We have a rectangular pyramid. So all of our sides will meet up in a point at the middle. We have edges of 6 and 8 and we have a height of 4. Okay, so we're looking for the surface area. Yes, technically there is a formula to find the surface area of a rectangular pyramid, but it is so much more complicated than finding just the area of each of the sides and adding them together. So let's just start with the base. That's the easiest one. It's a rectangle, it's 6 times 8, which is going to be 48. So I'm going to write that over here, and so as we add values, I'll just add them over here. Okay, so now we have to find the area of the triangular faces. And so we only have the base, and we need to find the height, so we can multiply and get the area, right? So the way that we can do that is, since our height of 4 is drawn exactly down the middle, let's draw a line out to the left here, connecting it to the middle of this side of 6. And we know that the length of this line is going to be 4 because it is halfway, it's halfway through the side of 8. I'm going to say that's 4. And so what we're looking for here is the line that goes straight up the middle of this face. I'm going to draw this face over here so we're facing it. So we have our face, base of 6, and then that line in the middle is the line that we're solving for. So we've created a right triangle here, and so we can just use Pythagoras to say 4 squared plus 4 squared is going to be 16 plus 16, which is 32. Find the square root of 32. Can also be simplified to 4 square roots of 2. So we know that the height of this triangle is 4 times the square root of 2. All right, so now we know how to find the area of a triangle. It's going to be our base times height divided by 2. Before we do that, let's just note that we have 2 faces of the same triangle that are completely congruent. So instead of dividing by 2 at the end, I'm just going to leave it and say that is the sum of those 2 areas. So 4 square roots of 2 times 6 is going to be equal to 24 times the square root of 2. So there's 2 more of our faces. I'm going to add that up here. 24 times the square root of 2. Now we're just going to repeat the process on our other face. So let's draw a line going from the center here, from where the height starts, all the way down to the middle of this side length. And then we would draw a line down here. It's kind of hard to see because it's straight down the middle, covers our other 2 lines. So I'm going to draw it over here. We have our base of 8, and that is the value that we're looking for. All right, so we know that this value coming from the middle to our side length is going to be 3 because it goes from halfway of our side length 6. So 3, height of 4, and instead of doing the Pythagorean theorem, we know that a 3, 4, 5 triangle is one of the primitive Pythagorean triples. So we can say that this length here is going to be 5. I'm going to do the exact same thing again as I did on this previous face. So we have 8 times 5. Instead of dividing it by 2 and then multiplying it by 2, we're just going to leave it at 40. So I'm going to add 40 up here. So you can leave it in radical form, but it has to be fully simplified. So we're going to say that 40 plus 48, since you can add those together, is 88 plus 24 times the square root of 2. Now you couldn't leave it in say your answer was the square root of 32. They would not accept that because it is not fully simplified. But this answer is fully simplified. You can multiply it out and add and then round to the nearest 4 digits, but I'm just going to leave it in radical form for now. So that is our final answer. Okay, here is our 4th and final 4-pointer of the video. The volume of a right hexagonal pyramid is 48 times the square root of 30. The side length of the base is 4. Find the height of the pyramid. Alright, first things first, I'm going to draw this so it's so much easier to visualize. So here's our hexagonal base, and there is the tip of our pyramid. Obviously that's not super well drawn, but it gets the job done. We know that our volume is 48 times the square root of 3, and we know that the side length of the base is 4. So to find the volume of any pyramid, there is a given formula. It would be volume is equal to 1/3 times the area of the base times the height of the pyramid. But in this situation, we don't have the area of the base. That's okay. We could hypothetically find it, but there's a formula that finds the volume of specifically a hexagonal pyramid that will help us so much more with this problem. That formula is the volume of any hexagonal pyramid is equal to the square root of 3 over 2 times a squared times h, where h is the height of our pyramid, which I will draw here since that's what we're trying to find, and a is the length of one of the sides of the hexagon if it is a regular hexagon, meaning all of the side lengths are the same. So, using this formula, we can plug in the information that we have to then solve for h, our height. So we know that our volume is 48 times the square root of 3, and that's equal to the square root of 3 over 2 times 4, the length of one of our sides, squared, times h. We simplify this a little more. 48 times the square root of 3 is equal to, so this is 16, and we divide 16 by 2, so 8 times the square root of 3 times h. Divide both sides by 8 times the square root of 3, and you are left with 6 as our height. And that is your final answer. Alright, here's our first 5-pointer of the video. Two circles are concentric. A chord, c units long, of the larger circle is tangent to the smaller circle. Express the area between the two circles in terms of c. Okay, let's start with a little defining here. So we have two circles that are concentric. Concentric means that they share the same center. For example, let's draw two circles. This dot is their center. It is the center of both of these circles. It's just two shapes, two anything, centered around the same point. Next, a chord. Okay, so let's say we have a circle. A chord is a line segment that connects any two parts of the circle. That's basically it. And then, if we have a line that is tangent to our circle, that means that it touches only one point on the circle. So it's very hard to draw, but let's just say that only touches one point on the circle. Okay, so now let's combine this. Let's say these are our two circles. We have our bigger circle and our smaller circle around the same center. We have one chord of this larger circle that's also tangent to the smaller circle. So I'm going to draw a chord that touches the smaller circle in one place. Like that. Okay. So I'm going to erase these just so we have more room to do some work. Okay, so in order to find the area of any circle, the information we need is a radius. So to compare the areas, we're going to have to find the radius of both the smaller circle and the larger circle. And how are we going to do that? Okay, so first, let's take the center point and use the smaller circle. I'm going to draw a line that is perpendicular to our chord, or to our tangent line of the smaller circle. So that is perpendicular, right there. And that, we're going to say, is radius 1. It's equal to the radius of our smaller circle. Now, we can draw a line from the center to any point on this larger circle, and that will equal the radius of the larger circle. But I'm going to draw the radius from the center to the end of the chord here. And now that means we have a right triangle, and our hypotenuse is radius 2. And I didn't label this in the beginning, but this chord is C. So now we have a right triangle, and okay, how can we compare all of these values? Well, we can use the Pythagorean theorem. So we know that R2 is our hypotenuse. So R2 squared minus one of our legs, R1 squared, is going to be equal to our final leg squared. And no, it is not going to be C. It is going to be C over 2 because C is the length of this entire chord. So R2 squared minus R1 squared is going to be equal to C over 2 squared. Okay, so now that we have a relationship between our two radii and our value C, let's figure out how we're going to compare the two areas. So we know that the area of one of these circles, well, the area of both of these circles is equal to the formula area is equal to pi radius squared. Okay, so if we're comparing the areas of these two circles, we can say that the area of the larger one is R2 squared times pi, and then since we're finding the difference, the area around it, minus R1 squared pi. That's equal to the difference of the areas. So now I'm going to take out pi and say R2 squared minus R1 squared, all multiplied by pi. Now, you notice we have this, which is equal to this exact value up here. So now I'm going to substitute C2 squared for R2 squared minus R1 squared because we're trying to find the difference areas in terms of C. So we're going to substitute that, and I'm going to bring it over here, and we'll say pi times C over 2 squared. We can distribute the squared and say pi times C squared over 4, and that is your final answer. Now, I know it's a little bit of a strange one. Conceptually, it's kind of weird, but I think it's a very fun problem. So let's move on. Okay, here's the next problem. A spherical balloon has a volume of 288 pi centimeters cubed. If it begins losing volume at the rate of 18 pi cubic centimeters per hour, how many hours will it take until the number for its surface area equals the number for its volume? Alright, so I'm going to draw our spherical balloon here, and we're going to say, okay, 288 pi is our volume. We want our volume to end up equaling our surface area as it reduces by 18 pi every hour. So since 18 pi is in cubic centimeters, the way that we're going to subtract that is just subtracting 18 pi again and again from 288 pi. So for example, after 1 hour, the volume of the balloon is going to be 270 pi. So we want our volume to be equal to our surface area after a certain amount of hours. So the way that we can set that up is by saying, okay, surface area is equal to volume. The one piece of information in both of those that we actually get from the circle or from the sphere itself is the radius. So I'm going to write the formula for the surface area and set it equal to the formula for the volume. I'm going to do that because we can then simplify for our radius, and then that kind of gives us our target radius, which is going to be the radius in which the surface area is equal to the volume. So we have 4 pi r squared is the surface area formula, and we have 4/3 pi r cubed is equal to our volume. And again, by doing this, we solve for our radius, which is when the surface area and volume are going to be equal. So pi cancels out on both sides. We can divide r squared from both sides, and so we get 4 is equal to 4/3 r, multiply 3/4 on both sides, and we get that 3 is equal to r. So this is 3 is what we want our radius to be equal to. So now that we have our target radius, let's find out what the volume is when our radius is 3, so we can find the difference between our target volume, where our radius is 3, and our current volume. So let's plug 3 into our volume formula. So we have 4/3 times pi times 3 cubed. 3 cubed is 27, divided by 3 is 9, times 4 is 36, and don't forget about the pi, so 36 pi is our volume when our radius is 3. So, if we start with 288 pi as our volume and get to 36 pi, all we have to do is find the difference and divide by 18 pi. We're going to divide by 18 pi so we can get the amount of hours, because you're subtracting by 18 pi every hour, so that gets us the amount of hours. So 288 pi minus 36 pi will get us 252 pi. 252 pi divided by 18 pi is going to equal 14. So our final answer is going to be 14 hours. Let's move on. Okay, here's our final problem of the video. Find the volume of the largest cube that can fit inside a sphere of radius 6. State your answer as exact or rounded to 4 decimal places. Okay, again, this is another pretty weird one to visualize. So I'm going to start by thinking about it in 2 dimensions. Let's say instead of sphere it said circle, and instead of cube it said square. So we have our circle, and we have the largest square that can fit into this circle. We have our given radius of 6. So at any point, even if I go to the corner of the square, it's going to be 6. So from that, we can say, oh, okay, we draw a straight line down as the diagonal of our square. That's going to be 2 times our radius, so it's going to equal 12. Okay, so let's apply that to a sphere. I'm going to keep the same drawing because it would be very difficult to draw a cube inside a sphere. So we have our sphere and we have our cube. We know that, again, the longest diagonal in the cube is going to be 12. From the furthest corner to the very opposite corner, that's going to be 12. Also, the way that we can find the value of the side length, since we're going to get the diagonal, how are we going to get the side length? Okay, you could solve it out, but as I mentioned previously in one of the 3-pointers earlier in the video, when you have a triangle, a 45, 45, 90 triangle, the ratio of the side lengths are x, x, square root of 2 times x. A similar thing applies to cubes. The side lengths, if they are equal to x, the longest diagonal is going to be equal to x times the square root of 3. So if we know that our longest diagonal is going to be 12, and we also know that our longest diagonal is equal to x, our side length, times the square root of 3, we can set those equal to each other and solve for our side length of x. So we have 12 is equal to x times the square root of 3. Divide the square root of 3 on both sides, you get 12 over the square root of 3. You can simplify that so you get the radical out of the denominator. Multiply the top and bottom by the square root of 3. You get 12 square roots of 3 on top divided by 3 on the bottom. Simplify the 12 and the 3, so you get 4 times the square root of 3 is equal to x. X is our side length of the cube. Now, all we have to do is say 4 times the square root of 3 times 4 times the square root of 3 times 4 times the square root of 3 to find the volume of this cube. So we have 4 cubed, because it's going to be 4 times the square root of 3 cubed. 4 cubed is 64 times 3 cubed, which is 3 times the square root of 3, and so we get 192 times the square root of 3. And that is our answer as an exact answer. We would just leave it fully simplified as 192 times the square root of 3. Or, since this is an active calculator round, you can plug in 192 times the square root of 3, which is equal to, and we have to round to 4 decimal points, 332.5538. And either one of those is an acceptable answer. But there we go, last problem of the video. Alright, this is our video on meet number 2, topic number 5, areas and volumes.
Thank you for watching.
I'm Iris.
And I'm Sebastian.
And we are the MAML Manual.